Good afternoon, everyone. And I'd like to get the show on the road. I'm Robert Merton, and I have the great pleasure and honor of introducing the speaker this afternoon. I'll make it really very short. Before I forget, if anyone has a cell phone or laptops, unless they're taking notes, if the phone rings, I'm going to assume it must be for me. Okay, thank you. Well, as you probably know, our speaker, Robert Litterman, is the inaugural recipient of the Sussman Award. As what comes with that award is the, I hope not obligation, but the fun of giving a series of public lectures here at MIT. And the first one he gave last September involving climate. Today is the second. And it's going to be on two applications of his work, and he's probably best known for, but I'll let him judge that, in using informative Bayesian approaches, vector analysis for both estimating expected returns, asset pricing returns, and doing global asset allocation, and that's the Black-Litterman model, and then also to economic forecasting with vector autoregression. So I'd say a few words about where he's been. I expect many of you know. Certainly all the students here have taken the investments course surely know, because they still have to learn Black-Litterman as not historic reasons, but rather for basically state of the art. So I would open with that, and I mean I will talk about his formal appointments, but certainly the work that he did in developing the sort of Bayesian approach to an equilibrium Bayesian approach to estimating expected returns and risk, and therefore being able to do asset allocation, at the time was really quite innovative and very, very practical. There are many things that we do in research and academia that are interesting and we learn from them, but don't always have as immediate applications. This was one that does. It did, and still does. And on the still does, this was what, your paper was published 21 years ago? And that means the work, I suspect it was being used before you published it, right? Yes, that's always the case. So we're talking about close to a quarter century ago. The fact that it's still used today widely and thought of as being, state-of-the-art type of work is a testimony. There's not much that's done that has that longevity, particularly in practice. So I point that out. He was a partner at Goldman Sachs for 23 years or so, and I guess you were made a partner in 1994. He was in charge of risk management, worked on a whole bunch of things with Fisher Black and others, and created a whole bunch of people at Goldman who went on to do good things in their own right. He is now chairman of the risk committee of Kepos Capital and has a variety of other activities, which I won't go and name, but he's a broad person with lots of interests. So with all of that, I think I'll just say, welcome, Bob. We're looking forward to hearing from him, if you'll join me in.
Bob, thank you very much.
I'll turn mine on.
Thank you very much for that kind introduction. It is a pleasure to be here. When Andy asked me whether I'd be willing to accept the S. Donald Sussman Fellowship, he explained that it required 3 lectures. And I don't know if their obligations are fun, but it certainly was a little daunting. And I thought, well, I have one good one. Let's see if I can come up with 2 more. So I figured, since I am certainly best known for the Black-Litterman asset allocation model, that you'd probably want to hear about that. And as I thought about what I would say, it occurred to me that Black-Litterman was really an application of the same basic idea that I had used in my PhD dissertation. So as Professor Merton mentioned, Black-Litterman is already 20-some years old, and my PhD was a dozen years before that. So these are kind of historical ideas, and I'll present them as that. I don't want to suggest that, well, They are still being used for sure, especially the Black-Litterman model. I think maybe the Bayesian vector autoregressions could be used more. But they're not new ideas, and I don't claim that they're on the frontier of econometrics or anything like that. But I think they are kind of very practical. They've been useful to a lot of people in a lot of contexts, and what I guess I would hope is that by focusing on the basic idea behind both of these applications, maybe there's folks here who are facing different problems today who would say, maybe I could apply that same basic idea in what I'm doing. And the idea was pretty simple, originally as applied to Bayesian vector autoregressions. And maybe just before I go too far into it, I should say that I was very lucky in my career to have worked with some very smart people, including my advisors at Minnesota, and it was really my advisor Chris Sims who suggested applying this approach to Bayesian vector autoregressions, and then my colleague Fisher Black at Goldman Sachs who suggested applying it to portfolio construction. So my role was really more of a financial engineer, a young kid who could program in Fortran in those days and actually make it work. So with that as introduction, I would say the basic idea is in both of these applications, you're trying to find a very weak signal in noisy data. And so you're kind of trying to tune it in. And what the Bayesian prior does is it's a way of imposing a little bit of structure, but in a way, hopefully, that is more flexible than simply imposing a constraint or a fixed structure. And I think the applications will kind of show how that works. But just to give you a sense of what's going on, and this is a very old equation. It's the only equation in this presentation. So it's what's called the Tile-Goldberger mixed estimation formula. It was relatively new, but already in the textbooks when I was studying econometrics. So it's over 50 years old today. And in fact, many of you may recognize it as a special case of the Kalman filter. So there's really nothing new here. It's just this is how you combine information. And what made it useful in those days was, we didn't have all the computing power that we have today. So this was a formula that said, if you can express a prior as a set of data, this tells you how to combine it, your prior with the data and come up with a posterior mean estimator. Now there's many ways of doing this more completely today. You can do Monte Carlo integration and so on. But what was very nice was the convenience at the time of being able to combine a prior with data. And then what I kind of tried to do was think about, well, how can we use that framework to come up with practical solutions? And so the two applications are in portfolio construction. That's Black-Litterman in 1989 with Fisher Black. And the insight there, what's incorporated into the prior, is that the global CAPM equilibrium provides a neutral perspective on expected returns, and then we can tilt away from those. And it turned out that was a very useful way of thinking about portfolio construction. The earlier application was in macroeconomic forecasting. This was my dissertation, again with my advisor Chris Sims, and the idea, we called it Bayesian vector autoregressions. The idea was that most economic time series, appropriately filtered, look like random walks with trends. And you can use that insight to try and capture the cross-variable effects, which are very difficult actually to estimate very well by using a prior appropriately. Now I'm going to start with the Black-Litterman asset allocation model. And I'm not going to derive it or anything. I'm just going to try and use show you a simple example that will illustrate how it works. So basic idea is start with a prior that the CAPM equilibrium, I don't know if I should assume you're all familiar with that, but I'm obviously not going to derive that as well. Fisher had developed a global version of the CAPM. The CAPM basically says, in the simplest possible world, a one-period world, it's not trying to be realistic, but what would happen if all agents were optimizers in terms of maximizing expected return, minimizing volatility of their portfolio. What would be the equilibrium expected returns that would cause the demand for assets to equal the supply? And the real insight of CAPN, I would say, was that it turns out that in this context, the risk premiums are not a function of the volatility of the assets, but rather a function of their covariance with the market portfolio. And it's clearly too simple of a model to be taken very seriously, but it has a lot of insights. It's a very simple model, and it really provides, I think, a very good intuition for the more general situation that I think we realize exists, which is, dynamic economy, one in which what's important is not really the returns on the market portfolio, but the marginal utility of agents in that economy. And so rather than the covariance being with the market portfolio, more generally, it's a covariance with marginal utility. But it turns out that there's, the simple version of it is very useful. And even though the empirical evidence on the CAPM, I would say, is very mixed, the beauty of Black-Litterman, if you will, is that the whole point of it is to combine that equilibrium, that neutral starting point, with one's views about where are these opportunities, these disequilibrium. And in practice, as you probably all know, it's actually quite difficult for investors on average to outperform the market. The market is, after all, the sum of everyone's investments, and given transactions costs, fees, and so on, very few investors actually outperform the market over time. So that is a nice, from a practical point of view, kind of target. Let me see if I can outperform the market by tilting away from it. I was actually sort of given that assignment when I was at Goldman Sachs in a rather difficult context, which was global fixed income portfolios. This goes back to the late 80s when Japanese investors had a lot of wealth. They were trying to invest globally in fixed income portfolios. And so I was given this assignment. And it turns out that, as is well known, mean variance optimizers tend to be relatively badly behaved. And in particular, in this context of global fixed income, because you have so many highly correlated assets. Bond markets move together globally, and we wanted to also incorporate currencies, and currencies as independent risk factors, and currencies are highly correlated. So my starting point was to program up a standard mean variance optimizer to put in the Goldman Sachs economists' forecasts. They very regularly would publish forecasts of bond yields globally for the next 3 months or longer, currency exchange rates. And I built this nice front end where you could put in those forecasts and optimize and see what came out. And it turned out, it looked rather bizarre. And even worse, if you would change those bond yield assumptions, even by, say, 5 basis points, you'd get completely different portfolios. They were very sensitive relative to what would be a realistic degree of precision from the forecast. And so I went to Fisher and said, these models are very badly behaved. And I was surprised by his response. He said, well, that's well known. And what surprised me is he had suggested that I use that model. So I said, well, what do we do about that? And he said, well, why don't we build in this global, I've been working on this global equilibrium model. He called it universal hedging. And what was also kind of interesting is I'd seen this paper just a few weeks earlier while I was working on the optimization problem, and I thought, well, this has nothing to do with it. I'll come back to it, But that was part of Fisher's genius. His global universal hedging paper was focused on what's the right amount of currency to hedge in a global equity portfolio. So it wasn't obvious that it had anything to do with asset allocation, especially in fixed income. But when he suggested that, I did sort of recognize that, well, it had some similarities to what I had done before, and we could build that global equilibrium in as a prior. We could deviate based on views, and it just turned out that provided a tremendous amount of flexibility. Now, one thing I want to emphasize at the outset is you can't test Black-Litterman. It's not a model that generates its own forecast. People have often asked me, how do you test it? All it says in the absence of external views is hold the market portfolio. So any test of Black-Litterman would have to be a test of the views that someone is putting into it. And there's really, Black-Litterman has nothing to say about where these views come from. But I'm going to give you an example to illustrate the flexibility and how you might think about this framework as being helpful. And so let's consider an objective here is to build a portfolio to benefit from momentum in global equity markets. Now, momentum is one of those deviations from equilibrium that we don't have a great explanation for. It's just regularity that we've seen in not only equity markets, but many markets around the world for a long period of time. There are some behavioral explanations, or some explanations in terms of friction and incorporating information. But basically, the idea is that assets that have been going up tend to continue going up in price, and vice versa. Those that have been performing poorly tend to continue performing poorly. Now, you wouldn't expect that to continue because it's so easy to measure, and we keep expecting it to sort of diminish or go away, but so far that hasn't really happened. And so I'm not going to try and explain it, although that's certainly an interesting thing to do that many people have done. I'm just going to say, suppose we observe it, and I'll use a very simple measure of momentum. How would we try and take advantage of it? And I'll contrast a sort of standard approach using mean variance optimization versus using Black-Litterman. And so the basic idea of a traditional approach would be to say, what I need to have as inputs into this optimization exercise is a covariance matrix of returns to measure volatilities and correlations, and a set of expected return assumptions. And so with respect to momentum, I'm going to assume that the excess returns going forward are proportional to this measured momentum, how much return I've seen, say, over the previous year. That's going to be my simple measure. Now, it turns out that's what I call here a relatively strong set of assumptions. If you have n assets, then you have n assumptions that for each asset, the expected excess return going forward is going to be proportional to this momentum. And in particular, those forecasts ignore anything about the covariance. And what we're going to see is that in the optimal portfolio, to the extent that there seems to be bad behavior, what you're really capturing is the inconsistencies between the expected return assumptions and the covariances. So in Black-Litterman, what having that equilibrium prior does is it allows you the flexibility not to have forecasts for every asset. You can have as many views as you want or as few as you want. And so I'm going to give an example where instead of assuming that all expected returns are proportional to the momentum measure, the portfolio that has long positions in assets that have high momentum and short positions in assets that have low momentum or negative momentum will have a positive return. It's one assumption. It's a weaker assumption. And then I'm going to let the covariance matrix tell me what are the expected returns that are as consistent as possible with that one weaker assumption and the covariance matrix that I'm using. It may or may not be a better assumption. You could look empirically at which of these assumptions makes more sense, and there may be a third or more assumptions. What Black-Litterman really has done is transform the question into forecasting n expected returns to what do you really know about this data? And that is a way that is likely to give you, I think, better behaved portfolios. Now, here are the measures of momentum as of January 2013. Hong Kong was the best performing market basically last year, Brazil the worst, and you can see how they're ranked. So the basic idea is we should assume that countries like Hong Kong, Switzerland, Germany are going to perform better than Japan, Spain, Brazil. And again, if you do the traditional mean variance approach, a natural thing to assume is that returns going forward are going to be proportional to these historical returns. In fact, if you make that assumption, put it into the optimizer, then these are a set of weights that come out as the optimal portfolio. And what I'd like you to focus on in particular are how close these sort of intermediate countries are, the US, UK, India, France. They all have very similar expected returns, and yet if you look at the optimal portfolio, the weights are very different. And what's going on there is what the optimizer is doing is saying, well, these a number of these assets are very highly correlated. There's slight differences in expected returns, and I can, by adjusting these weights, have very little impact on the total return of the portfolio, but reduce the risk. In effect, I'm going to be hedging the risk by going long one and short the other. And in fact, if we go into the data and look at what's going on, we find 5 different pairs here that have high correlations, very similar returns, and end up hedging each other. So for example, the UK, it turns out, is very highly correlated with both, with the US. Canada is also correlated with the US. So we end up taking a long position in the US, which has slightly higher expected return than the UK, virtually no position in the UK. In other words, relative to what you might expect, equal positions. We're long the US, short the UK, and similarly short Canada. And this is going to give us a slightly higher expected return with slightly lower risk than a portfolio that might have smoother weights. Now in Black-Litterman, you've got this equilibrium, so that's a starting point. The equilibrium is basically the set of expected returns that justify holding the market portfolio. So mu is going to be our vector of expected returns, and we're going to assume that it's basically, simplest assumption would be normal with a set of expected returns pi that are basically those that would generate the market cap weights. In this case, W is going to be the market cap weights, and basically you're inverting the formula for the optimal portfolio weights and saying it's going to be proportional to this matrix equation, lambda sigma W, where W are the weights and sigma is the covariance matrix of returns. So basically this is the assumption that expected excess returns are proportional to beta, or covariance with the market portfolio. And the intuition there is very simply that in the market portfolio, which in equilibrium everyone holds, the marginal contribution to risk is proportional to beta. So that's what you should be getting paid as a risk premium. Well, then in addition, we're going to add a set of, yes? Oh, I'm sorry, tau is it's just a scale factor, and the assumption there is that, I didn't go into this, but we're treating these expected returns as a random variable. It's kind of an unusual way to think about them, and we're saying that the covariance matrix of the expected returns, if you will, is proportional to the covariance matrix of actual returns, but it's going to be much smaller. Actual returns have large covariance, large uncertainty relative to what the mean return is likely to be, but we're saying if two variables returns, or if two assets returns are very highly correlated, then it's likely that their means are highly correlated. If one is higher, the other is likely to be higher. So that seemed like a natural assumption. So the additional views really can be anything, but an example of an additional view would be to say, if we have a portfolio where the weights are linearly related to the ordering of the momentum, or more generally of a factor, we think that portfolio will have a positive expected return. And that positive expected return would be given by Q. Omega is in general a matrix when you have multiple views, but in this case it's just one view, so it would be a scalar, basically reflecting the confidence that you have in that view. How much weight do you want to put on that view versus equilibrium? And that defines a dimension that might be an interesting dimension to look at. More generally, you might find the allocation of risk across multiple factors to be an interesting way to think about a problem, and then you have that freedom in Black-Litterman to more or less say, how do I want to allocate my deviations? How do I want to tilt away from equilibrium? And then we have a formula that combines the prior with the views. Now notice that my views are my data in this sense. It's not really a classical sort of econometric problem where you have data. The views, we don't specify where they could come from. In many contexts, they do represent some sort of estimation of returns, and they can be quantified from data, but more generally, we don't say where they come from. Now, if you do that combination, you get a frontier of portfolios that's illustrated here. If you have very low confidence in your view, that's the blue bars, then your optimal portfolio is basically that represents the market cap weights. So you see a big weight in the US, the largest. These are, by the way, the 15 largest equity markets around the world, and these blue bars are basically proportional to market cap weights. As you put more weight on your view, the red, the green, and then the purple bar, you move kind of smoothly from, although not necessarily linearly, from the market cap weights to the linearly declining weights that represent the view portfolio. And in fact, in a paper after Black-Litterman, we didn't quite realize this, but it became obvious later, that in a totally unconstrained environment, the optimal portfolio in Black-Litterman is a linear combination of the market cap weights and the view portfolios. So it's really very simple in that sense. And when we realized that, we also realized that, you know, what's the value added here? Because you're really specifying these view portfolios as well as the market portfolio. And so all this is telling you is what the weights are. And the weights are basically a function of the confidence that you have. Now, the answer to that question, I would say, is that in practice, you're usually interested in solving a much more constrained problem. So one where there are literally constraints, or there are transactions costs, or there are other issues that affect what you're doing, and you're starting with a given portfolio, you're updating it based on new information, and it's very helpful in that context to have an optimizer that you trust will give you a portfolio that makes sense in the unconstrained case. It's very hard otherwise to know whether we're moving in a sensible direction or not. And so if I compare these two portfolios, you know, you have the blue bars representing traditional mean variance optimization. You have the red bars, which in this case are a high degree of confidence on the one portfolio view. We don't know that one is necessarily better than the other, but in practice, it's very helpful to be able to specify a set of views that really reflects what you want it to reflect. You may want it to reflect that we literally think these forecasts of expected returns are proportional to momentum, or we may not. We may want to specify something much weaker, which then says, I'd like to think that those that have positive momentum are going to perform better than those that have negative momentum, but let me allow the covariance matrix to tell me something about how that's likely to play out. Or you might want to do something intermediate. So, you know, it really, I would say, is a framework that forces the investor to think about what information do I really want to bring to this problem, rather than thinking too mechanically about it as a pure forecasting problem. Let the data tell me. So now let's turn to Bayesian vector autoregressions. That, again, is a tool for macroeconomic forecasting. The basic plan here is to start with a data-driven representation of the dynamic properties of macroeconomic time series. We want to use minimal economic theory. We want to generate as accurate forecasts as we can. And then with this system, we're going to try and better understand the origins of the recent recession. For me, agreeing to give this lecture was a good excuse to go back and look at some data I hadn't looked at using a tool that was developed, you know, 4 decades ago or almost. And so that was kind of fun. I'll give you the answer, basically, which probably won't surprise many of you. But what we find when we use this approach is that housing was very much at the center of this recession. Probably not a surprise, although it's perhaps not as obvious as you might think. Just to give you a little bit of context, when this work was done, it was back at the University of Minnesota in the late 1970s, And at that time, most economic modeling was based on these large econometric models that had been developed in the tradition of what was the Coles Commission. There was a lot of concern about those, in part because they were very unwieldy. There were hundreds of equations. Those equations were based on basically the idea of trying to figure out what determines various demand and supply equations in the economy, and then writing down regressions that have what you think are the most important variables on the explanatory variables, and there was a school of criticism, rational expectations, that was very popular at Chicago and Minnesota, that said, well, it's very hard to exclude any variables from any of these equations, because when you take people's expectations into account, the consumption or the money demand or whatever, investment is going to depend on everything and how it fits together. And so the traditional approach of excluding variables, most variables from each equation, and just picking a few is not very well justified. And so my advisors, Tom Sargent and Chris Sims, who last year, by the way, won the Nobel Prize in economics, they encouraged me and others to think about relying as little as possible on economic theory and trying to just estimate what the stylized facts are in the data with respect to the dynamic interactions of economic variables. It turned out that was a very difficult effort. At that time, and still today, very simple univariate approaches to forecasting work quite well. And when you try to generalize those in these large econometric models, what you find is they don't work nearly as well. The out-of-sample forecasts, of course, they can fit in sample very easily, but out of sample, they tend to do very poorly. And so the Bayesian vector autoregressions were an attempt to address this issue. And we looked at forecast accuracy as kind of the first order measure of success. Could we improve the forecasts from a univariate specification by bringing in cross-variable information? And that was difficult. Now, there are very important limitations of this approach, which were well recognized. I'm not going to spend a lot of time on that, but just recognize that these are what we call reduced forms. They don't really, they are consistent with whatever structure there is in the economy, but they don't tell you what's going to happen if you change something in the economy. They're just the net result of everything interacting. And so in particular, if you think about policy interventions, I'm going to hold some things fixed and then I'm going to change something, monetary policy or fiscal policy or regulations of some sort. These don't tell you what to expect. I'm going to try and look at the Great Recession. So I'm focusing on the various components of GDP, as well as a couple of financial market variables. So I actually started with just the S&P 500, but then when I presented this paper a couple of months ago, one of the reactions I got was, well, can you separate out equity wealth from non-equity wealth? In particular, basically, for most households, that's going to be the value of their home. And so I've taken the flow of funds data and divided it into equity assets versus non-equity assets, which basically you can think of as housing values. Also, there's a lot of fixed income in there, but most of the volatility of that non-equity assets variable is going to be housing. And in addition, I have bond yields, credit spreads, and the price level. Now, the reason that a number of people have actually said that they don't believe that housing was central is illustrated in the Great Recession, is illustrated in this slide, which basically shows the time series of the components of real GDP, as well as the top line itself is real GDP, the total. And what you can see on this graph, first of all, is that obviously the Great Recession was the dominant event during this last, whatever that is, 25 or so years. And the component that looks, 2/3 of GDP is coming from consumption. and it's a little bit smoother than GDP. But then if we look at, well, where's the rest of that volatility coming from, the green line there is non-residential investment. Housing is this yellowish or orange line, and it peaks back in 2005 or so. It's not a very volatile component. It starts coming down for sure, but even at the peak, it's about 6.5% of GDP. At the recent trough, it was about 2.5%, and just visually, it doesn't look like that explains much about the recession. It looks like it must have to do with investment and consumption. The blue line right above the green one, right above investment, is government spending. Looks like that doesn't explain much. And then you have net exports, the purple line, that goes the wrong way. That's coming back, increasing during the recession. Okay, so let's see what these Bayesian vector autoregressions tell us. Now, the first thing we're going to do is try and find a specification that does well in out-of-sample forecasting. And in order to do that, we want to define an objective function that makes sense. And so I'm going to, first of all, define units. I want to average across all these variables. And so at each point in time, from 1961 to 2012, I'm going to generate basically a measure of the innovation standard deviation at that time. I'm going to use data up to that time, data starting from 1948. So I get this sigma IT. For each variable, I know what a 1 standard deviation surprise is. And then I'm going to measure for a variety of models, how many standard deviations is that shock in the context of this model. So this is just to define units. And then for a model, so a model is going to be like a 1-lag univariate or one lag regression, autoregression, yeah, a 2-lag autoregression or a Bayesian vector autoregression. So I have various models, M, and I'm going to have 10 variables, and I have K forecasts, K being steps ahead. So from 1 to 8 steps, and I'm going to weight these, actually giving them declining weights, so that my average weight is about 3/4. I'm sort of trying to look out forward, up to 2 years. I'd like to have more focus on the longer forecast because I'm interested in forecasting further out into the future, but obviously I have fewer observations. Often we just focus on the 1 step ahead forecast, but I want to put more weight on longer term, so I'm kind of just defining this objective function that weights those. For each forecast, the forecast error is obviously the difference between that and the actual, and then I'm going to scale it by a square root of k times the innovation standard error. If these were random walks, that would be and the error grew with the square root of t. That's what you would expect in order to get it all into sort of how many standard deviations are each of these errors. And then my objective function is going to be to minimize these scaled forecast errors. And so basically I just define a scale factor. So again, units are an average number of standard deviations across variables, across time, and across different horizons. And so that gives me finally an objective function. I call it omega. So I'm going to get a measure of forecast accuracy for each model. And then I'm going to compare these and see what I can do. Now, one thing to recognize is that these volatilities do change over time. And so this is the average mean square error across all variables for each quarter from 1970 through the present. A 1 here would be what you would expect. And because I'm going out 2 years in terms of my forecast, these are correlated over time. But you can see there were periods of volatility relative to the previous innovations back in the early 70s and the early 80s. But up until about the mid-90s, you could definitely suspect that the volatility of these components of GDP and financial variables was declining. Some people talked about the Great Moderation, and it was sort of looking at data like this. But then you notice 2000 and beyond has, that volatility obviously has reemerged. And so that just gives you a picture of what's happened. Let's start with these univariate autoregressions. They're simple models that are hard to beat. They don't tell us much about what's going on in the economy. But we use these simple univariate regressions. We create these forecasts, and we look at what has been the measures of forecast error over a 40-year sample starting from 72, and the 4 subperiods representing 10 years each. And so what you see here is, okay, a 1-lag autoregression. 1 lag is not enough. That has almost 2 standard deviations of forecast error over the whole sample. If we go to 2 lags, we get a dramatic decrease down to 1.55. If we go to 3 lags, it goes down to 1.48, so it's a little better. And then 4 lags, it's just very slightly better than that, but it seems to be flattening out. I didn't bother going more than 4 lags, and I've highlighted in red where the best resulting model was. So that's where we're starting. We're going to try and beat that. I tried something else that kind of comes out of the financial markets. You've probably heard of technical analysis. Well, technical analysis is basically just looking at when different moving averages cross each other, but it's actually very similar to running these autoregressions, except rather than having individual lags, you compare where you are today versus moving averages. And so it's a nice way of maybe compressing the data a little bit and separating it by frequency. So if you think, gee, high frequency is important, low frequency is important, it allows you to separate that a little bit. It turned out it really didn't matter much, but it was something that I was experimenting with, so I want to report the results here. The 1 lag is the same because you start with where you are most recently, and then instead of regressing on further lags, you regress on these different moving averages. So I have a moving average with a 2-quarter half-life, a 4-quarter half-life, and an 8-quarter half-life. And what I found is, well, the 2-quarter half-life does significantly better. In fact, it does better than any of the simple regressions on past lags, a little bit better than the 4-lag autoregression. But then when you add a 4-quarter and 8-quarter, those don't help. In fact, out of sample, they make things a little bit worse. So now I've got these 2 univariate models, and I'm going to see what happens if we try and allow cross-equation information to come in. As I mentioned, if you just use an unconstrained vector autoregression, there's too many free parameters. In a univariate 4-lag equation, you have 5 free parameters because you add a constant term. In an unrestricted 4-lag vector autoregression with 10 variables, you have 41 coefficients to estimate. And if you just do the standard out-of-sample forecasting exercise, instead of having 1.47 standard deviations as your average error, it jumps up to 1.77. So it's 24% worse. When I was at the University of Minnesota as a graduate student, and my advisors were saying, why don't you try vector autoregressions? I came back and I said, they don't work. And so Sim said, well, have you tried Bayesian shrinkage? And I said, no, what does that mean? And he suggested, well, why don't you think about creating this kind of dimension where you shrink things towards 0 and see if there's an interior point that's better than either of the ends. That was the basic idea. So I create a prior that says all these coefficients on other variables are centered around 0. I'm not using any economic theory per se. I'm going to have a little bit of flexibility in that prior. I parameterize it by these 2 parameters, other and decay. Other is a parameter that says how much uncertainty is there about the first lag of each of these other coefficients. And then decay is a parameter that says, given that uncertainty about the first lag, how much less or how much more do you want to shrink additional lags? Basically, your idea is it's most likely that the most recent value has the most information and less likely that other lags will have information about what's going on. So the prior says that for lag j of variable k in equation I, that coefficient is centered around 0. And the larger this parameter other is, the tighter it is around 0, and the larger this parameter decay is, the tighter it is on further lags. It turns out the decay parameter wasn't very interesting because it got very large. The optimal forecasts were very tight around all these lags of other variables. What was interesting was the other, and we can think of a frontier here where we start at 0 on the horizontal axis with the univariate autoregression, and that's saying we're absolutely sure all these other coefficients are 0. And then how do the out-of-sample forecast errors change as we allow those coefficients to move away from 0? And the answer, as you would hope, is that things get better. You might be a little disappointed that they only get about 3% better at the optimal point. This is over the whole sample. That's particularly disturbing if you recognize now that we can't think of this frontier as being out of sample. We're now saying at the end of the sample, had we used this parameter other fixed at this point the whole time, this is the optimal point. But we wouldn't have known that at that time. So in order to really think about it, and by the way, so if you keep going further to the right on this graph, you eventually get to 24% worse. That's what I talked about before. So it quickly gets very bad. Now, if you want to make it truly out of sample, then what you have to do is say, let me assume that I will forecast at a time t using the best parameter up to that point in time. So this shows how that parameter other evolves over time if at each point in time you optimize and find the best parameter up to that point in time. You can see, for instance, here that starting around 2000, you had to get much tighter on these cross-variable interactions in order to get the optimal forecast. And so what I showed you on the previous graph is where we are today. Earlier on, we were more loose and allowed more cross-variable interactions. So what then do we get when we use that best hyperparameter, call it other, at each point in time? Well, we get a total error of 1.46 standard deviations, which is slightly better than any of the univariate autoregressions. Not as good, though, as the exponentially smoothed univariate equation. So it's not particularly inspiring, but there's slight improvement, at least out of sample. If we do the same basic exercise for the exponentially smoothed, and it's really the same form of prior, and do the same type of frontier here at the end of sample, we get about 2.5%. These two approaches really aren't all that different, and we get a similar pattern for the best coefficient at each point in time. And then if we look at using that out-of-sample hyperparameter at each point in time, the best system is actually this exponentially smoothed Bayesian vector autoregression, which also slightly improves relative to the 2/4 half-life and is slightly better than the simple Bayesian vector autoregression. So I'm going to take this exponentially smoothed system, and I'm going to say, well, what does it tell us about what happened during the Great Recession? So the first thing we look at is what we call innovation accounting, which is basically just what were the innovations over time? What were the surprises? If you take each of these variables and look at your forecast error one step ahead, what do they look like? Your assumption is basically they're going to be random, independent over time, not necessarily that they have constant variance, but this is not a model that has a model of time-varying volatility. So what we do see is changing volatility over time. If you look at equities, and this again is the equity component of wealth is what it really is, but it's very highly correlated with the S&P 500. You see that there were random innovations, not particularly surprising, up to about 2008, and really it was late in 2008. And you can see where the crisis occurred. It's particularly obvious with credit spreads. Also, I highlight that these vertical axes have different scales. So notice that the innovation in credit spreads in the fourth quarter of 2008 was 8 standard deviations. That was a huge shock. So that's when people realized, oh my God, the economy is coming apart. There were big innovations in equities and bonds as well, but there's not a lot going on 2005, 2006, 2007. If we look at the non-equity wealth innovations, again, basically housing, and then on the bottom graph here, you see the housing innovations. There, if you look carefully, there is something interesting going on. We were sort of basically in a housing bubble with surprises in both valuations and house building. This is, when I say housing, I mean the housing component of GDP. This is the construction of houses. And it's, you can't, there's positive innovations for what, 1, 2, 3 years in a row there. Very unusual, not particularly large, but very unusual in total, and a similar pattern with a little more volatility in terms of the value of housing. There's not a lot going on with respect to price level innovations. That's probably not a surprise, although it's kind of interesting. Since 2010, they're small, but there have been a lot of positive innovations since then. If we look at government spending, there's one not terribly large, not even 2 standard deviations, but one big one that stands out, the second quarter of 2009. That was, the stimulus. Since then, notice it's been basically negative. Consumption, you can very clearly see how we fell into that recession. It started a little bit earlier in consumption. It starts a little bit later in investments. And net exports looks kind of what you'd expect, pretty random. Now, if we're going to attribute the movements in GDP to these various innovations, we have to make an assumption about what we do with correlations. What you'd like to do is have some knowledge of the structure of the economy, but we're going to try and avoid making strong assumptions about that. But I show you here the correlation matrix, and for example, if we focus on the dark green, it's the largest positive innovation correlation in this matrix. It's between housing and consumption. So there is a very strong positive correlation between housing and consumption, and we have to decide, are we going to call that a housing innovation, or are we going to call it a consumption innovation, or is it something else? So what we're going to do is just define an ordering, and the variables that come earlier in the ordering are going to be, we're going to attribute the movements to those innovations. So we're going to say, basically, housing causes, or if you will, it's the housing innovation that causes this correlation between housing and consumption. It seems to me that's a natural assumption. It's unlikely that consumption, when there's a surprise in consumption, causes an increase in housing, but it seems very natural when people are building and buying and moving into new houses, they do a lot of other consumption spending. So more generally, what I've done is I've started with the financial variables because they're kind of forward-looking anyway, and I want to say, okay, if there's a movement up in the stock market, I don't know why, but it's probably anticipations of the economy is going to be better. So I'll call that the first shock, then the bond shock, then credit, then I get into the assets, inflation, and then finally the components of GDP, but I put housing first. Now, these are what we call the impulse response functions. These are basically the dynamics that are estimated in this system. You might call these the stylized facts. We haven't built any economic structure. And in this first slide, what I'm comparing are the standard Bayesian vector autoregressions on the left with the exponentially smoothed Bayesian vector autoregressions on the right. And this is the response to the first shock in the system, which is the equity valuation shock. And what you notice here is these look very similar. In other words, it doesn't really matter which of these systems you use. So I just show that comparison, although notice that there's a little bit more high frequency in the BVAR than there is in the exponentially smoothed one. Perhaps that high frequency is creating a little bit more noise. In any case, the exponentially smooth system had a better out-of-sample forecast error. So I'm going to focus on that system. And on the top graph in each column, I show the components of real GDP. The orange curve here is the total, so that's real GDP. And basically what this says is when there's a shock to equities, that precedes a positive response in real GDP of about 30 billion. So when you look at the top graph, it's important to realize the units are in billions of dollars. The bottom graph, the units are standard deviations, and those are the non-GDP components that are in this system. So this is an equity innovation. You can see starting at 1 standard deviation, and this is how the system responds to that shock. And then similarly, I'm going to go through these graphs pretty rapidly, but these are the stylized facts about how the system responds to a bond innovation, again about positive 30 billion in real GDP, credit spread. When spreads on lower rated bonds go up, that's a bad sign. GDP goes down. When this housing valuation goes up, non-equity assets, that's positive, but not particularly strong. It's basically a combination of consumption and investment. Price level is a little bit negative for GDP, but not very large. Housing, it turns out, is interesting because when you incorporate that consumption, innovation, it actually is larger in the first quarter than housing itself, because consumption is so much bigger, and that is a relatively good-sized innovation. When there's a housing innovation of 1 standard deviation, it's actually a $60 billion impact on GDP. Government innovations are about 50 billion, but remember they weren't very big. Consumption innovations are very large and very persistent, and the largest innovations are investment, but notice they're not nearly as persistent as consumption. And finally, net exports are basically relatively independent of everything and are about 40 billion. So now we get to kind of the bottom line. We start at 2002, the end of 2002, and we make a forecast. That's the red line. Not very interesting of itself, but that's how forecasts pretty much always look. You expect real GDP to grow there. And then we compare it to the actual. So what we're trying to explain is the deviation between that blue line, the actual GDP, and the forecast as of 2002. So this is what the deviation looks like. And we can break that down into what explains it. Well, if we start with the innovation starting in 2003, the first quarter, and we look only at the innovations in housing and the non-equity component of wealth, each of them is positive, and when you sum them, they basically explain what was going on. That's all you need to look at to understand why the economy was growing so strongly in 2003, 2004, 2005. It was totally housing. Now, it's also true, again, I don't think this is a surprise. In 2005, I remember listening to a presentation Bob Schiller made. He was talking a lot about the housing bubble at that time. He gave a very convincing lecture about how housing is overvalued by any possible measure, has never been this expensive before. And I remember sitting there thinking, well, okay, it sounds reasonable, but what do you do about that? You know, and we really weren't as focused as perhaps we should have been in retrospect. So as of the end of 2006, the economy appeared strong. This is a forecast. Actually, I've said that wrong. This is as of the end of 2005. So beginning of 2006, the economy appears strong. In fact, nothing much happened for almost 3 years, 2.5 years. And, but throughout this period, if we look at those innovations to housing and non-equity wealth, they're all negative. And so what did they imply? Well, if you just look at those two components alone, they basically explain over half of the deviation between that forecast and what actually happened. So that's the sense in which housing really explains most of what happened. Now, housing is very smooth. It didn't fall off a cliff in 2008 or 2009. It just started much earlier, and it was the cumulative impact of this negative impact on the economy that explains most of what actually happened. If we then look at what's left, and that's what the blue line in this graph is, this is the unexplained component of GDP, not explained by housing or non-equity wealth innovations. Most of that is explained by consumption and non-residential investment. Consumption first, that's the blue line here. Actually, I'm sorry, I misspoke. The blue line is consumption, the cumulative impact of consumption innovations. The red line is the cumulative impact of investment innovations. And then if we look at the sum of those, that's the red line here, and compare it with the unexplained component of GDP, it explains most of what's left. But notice the size of these, because if we look at the original, let me go back a few slides here, the deviation of the forecast from actual is 1.2 trillion. So that's the total shortfall, if you will, of GDP. Half of it, more than half, is explained by housing. Here, whoops, went the wrong way. Here what we have is about, what's left, 550 billion or so, and most of that is explained by consumption and investment. If we look at the financial markets, these are the cumulative impacts of equity innovations, bond innovations, and credit innovations. And again, units here are important. These are actually relatively small, although in total, they do explain a lot of the sharp fall in the fourth quarter of 2008. So what's left after you explain housing, after you take out consumption and investment, yes, there was a sharp collapse in the fourth quarter of 2008 that you could attribute to the innovations in these financial variables, but it's 250 billion, whereas housing was something like 600 billion. And finally, government spending. There's so much focus on government spending and what it's going to do to the economy, but over this period, it was really quite small. 50 billion, basically positive, basically due to that large innovation in the second quarter of 2009. So that's basically the story about what happened in the Great Recession, as you can learn about it from these basically atheoretical time series models. So in conclusion, the world is very complex. A lot of these signals are very weak, and it can be very helpful to think about some, let's say, structure that's not necessarily precise, and flexible ways of using it to gather and process the data. All right. I don't know if we have time for a few questions, but I'd be happy to take some questions. Yeah.
You're saying 800 billion in government spending reduced to 50 billion.
Did I get units wrong here? Where is it?
In a way, it was kind of the punchline that very...
Well, the innovation in government spending, you're talking about total government spending. Yeah. Let's go to these units here. Where am I? That's the graph I wanted to look at. So government spending here this is total government spending, the blue line, so it's about 2 trillion, I guess. And
you had those innovations, the actual bars.
Right, the innovations there, well, the bars I think were standard deviations. So this is a standard deviation. It was a 2 standard deviation innovation.
Sounded like they spent maybe this isn't what they allocated, but they actually got spent.
Well, a lot of what they did is sort of transfer payments. It doesn't show up in GDP. This is government spending, actually, on the economy. And so that, I don't know, if I look at this series, the innovation, really quite small. Yeah, the surprise. Remember, to the extent that government spending is driven by policies that are predictable, then it shouldn't even show up here. That should be built into the forecast. So this is the surprise relative to the forecast. Yep.
So in retrospect, what would you say to policymakers right around the Bush-Obama transition of what they got right, or maybe they did right, and some of the actions they did? What's the just one takeaway signal from this?
Well, okay, so my reaction to this was, it wasn't so surprising because I thought this was a housing event. And I still think it's a housing event. It's actually, what's surprising is sometimes how people say, well, it couldn't have been housing. Housing was only 5% of GDP or something. I think housing is very important, and that comes through with this data. Now, if you say, oh, what was the mistake? I don't think this analysis really answers that at all. But I would say that, yeah, the policies that encouraged housing, excessively encouraged it, and in fact created this whole, well, let's say it wasn't just policies. There were some policies, Fannie and Freddie, for instance, that were urged to support low-income housing. There was really the development of the mortgage market, which created an illusion that you could eliminate the aggregate risk from mortgage bonds, and that created a demand for mortgage bonds because they had higher yield and were perceived as having zero risk. They were rated AAA, they were insured, and you put them into structures where there was an equity component that supposedly took all the risk, and then these credit-enhanced components. So you had a lot of folks putting risky assets with aggregate risk into situations where they assumed there was no aggregate risk. And so that created an overhang of risk, which when it was recognized, led to the financial crisis. But it started in housing, for sure. Yeah.
So Bob, that was in a way the point I wanted to make, which is that your analysis of these Bayesian vector autoregressions follows very much the traditional macro view, which is to focus on real variables. What you didn't have in there were the financial variables, which you mentioned just now, and that is housing finance. And in particular, the most important aspect of housing finance was risk transfer and incorrect perception of risk exposure and leverage. So it seems like those are important variables to include in these kinds of macroeconomic analyses. Do you see any way of doing so? And have, when you were at Goldman as the head of risk management, presumably you use macro forecasts in some ways. Any hope of building those things into the traditional macro framework?
Well, I won't say no, but I think you have to be careful about what I'm trying to do here is not so much in the weeds. It's sort of from a high level, as you say, can we learn something about the basic components of GDP? And even in that context, I'm focusing on the lower frequency, if you will. Are they predictable? And one thing we learn is they're very hard to predict, actually. It's hard to beat a univariate. It's kind of, this isn't new in some sense because we observed this 30 years ago, but now we have 30 more years of data and we see the same basic pattern. There's not a lot of cross-variable predictability that we can bring in. It improves it a few % relative to the univariate. Also, I would say one of the things that I learned, if that's me or what, anyway, one of the things, one of the things I learned when I was in the business of making forecasts, and it's kind of a depressing thing, but what's much more useful, basically a lot of these variables do look like random walks. And in a random walk, knowing where you are is that's all there is to know. And in fact, for a lot of these macro variables, forecasting, if you know where you are, you have a big advantage. So looking at monthly data or weekly data is very useful, more than the low frequency components, which are really quite small. So now your question was a little bit more focused on were there aspects of the financial system. I was there, we didn't see them. The conventional wisdom in 2000, let's say 5, was that, yeah, housing is overpriced, but it's a very small component of the economy. I remember very vividly at a dinner, it was in December of 2006, and a hedge fund manager asked me, do you think housing, actually said, do you think subprime can take down the economy? And I thought, I don't know, that never occurred to me. I wasn't involved in housing at that point, so it wasn't my focus, but I had no idea really. Obviously, and you can read now some of these books about, Paulson and some of these other hedge fund managers who saw this issue, and they said, look, this is a disaster waiting to happen. And the book by Michael Lewis on this I thought was very interesting, and he actually talks about how Paulson came to Goldman Sachs and tried to convince us that the housing market was going to melt down, and we didn't believe it. And that was, I think, in late 2006. And then we sort of became convinced, and I saw that happening in early 2007. And then you started seeing this, strange things happening, problems in money markets, problems in credit, but it was all housing related, and it was all these mortgages that were in effect melting down, and people didn't want to recognize it, and people didn't know what it meant. And but meanwhile, 2 years earlier, the housing market had turned over and had been going down all this time. And so what we didn't recognize was how important that was, and how no one knew where and when and who was going to be the next. And in fact, the quants, I was a quant running a quant hedge fund at that time. We were the next ones to go, and we didn't see it coming. We thought we were totally independent of housing, but it turned out these connections were there, and we just didn't see them. So that's the topic of my next talk.
Keep it balanced. You talked about two things. I have a question about the first part.
Sure.
And you ended up, as you put it in a reduced form, you essentially come up with a weighting between the views and the market. Did you, as a matter of course, afterwards, do the time series returns to estimate at least after the fact? Oh, it's another power source. You're about to go out of energy.
Okay. Well, we're done.
Okay, but yes. But the question is, you would think that W, as you put it,
Yeah.
you can imagine fitting that W, finding the best W afterwards in the data. So answering the question, given what's happening, you didn't know from beforehand because you just had views, but you do have a process of weighting views against the market, and there's some mix. I would have thought maybe that you would look afterwards and do a post-analysis and say, how much should I have weighted it given the process? In other words, given the views and everything.
Yeah.
And then use that in some sense to inform your prior for how much to weight them as you went forward.
Well, what I tell you is what we did a lot of work on is how do we weight the different views? What should the views be, and how much weight do you give to them? The way the investment management business is structured, most investors make the decision on how much market exposure to take versus how much active risk to take. And so we were in the business of creating active risk, and we really didn't address what should be the appropriate mix between, call it active, deviations from the market versus market risk.
I guess it translates to somewhat the same thing, but I was just thinking of it in terms of
Forecasting.
making judgments as to how much weight I should put on the implied. And I can see you could have a sub-forecast, you have multiple inputs, so you have a vector of W's.
Right.
Then you could have done that too. The question was whether you, in some ways, because you have a long series, you have 20 years.
Right.
Whether you use that or not.
Yeah, well, I guess the answer is no. We didn't focus on that question. Yeah, it's an interesting question, but yeah.
Continuing on the Black-Litterman slide, when you showed us the covariance matrix for the expected returns, right, you
Right.
sort of modeled that as just a scalar
Right.
that would pull the measured covariances back. One could imagine trying to build a lot more structure into that covariance matrix with views about how the world had changed since the world you were estimating from and things like that. Did you in practice do much that got away from just using the historical covariance structure scaled back towards zero with a tau type factor, or because the second moment seems like it's where really the art comes in to try to figure out how you might try to do things on this side.
We did do a lot of work on estimating that covariance matrix, not so much on tau, but on the sigma itself. And that there is a lot of art to it. And a lot of it depends on what's your horizon, because obviously in investments, from a risk point of view, it's really what's going to be the volatility or the over the next short period until I rebalance this portfolio. And I mean, if there's no transactions costs. If there's transactions costs, it gets pushed out a little bit. And so there's a sort of subtle relationship there between transactions costs, between how quickly your signals decay, and how you want to optimally forecast volatilities and correlations. And we did do a lot of, and continue to do a lot of work on that. And where we're at today, I would say, is we used to focus a little bit on how quickly do you downweight old, how much weight do you put on recent versus older observations. Today, we sort of recognize that there's a state of let's say, of financial markets, or more generally of the economy. Sometimes it's volatile, sometimes it's not. And so we try and look at lots of different signals of, are we in call it a stressful period, or we call it our spillover model, because back during the crisis, a lot of things spilled over when there was high stress. And so we think about using a covariance matrix that represents the state of the world that we're in today. Is it a high stress world or a low stress world? And yes, we put more weight on more recent observations, but we also put more weight on older observations that represent this kind of a state of the world. Yep.
Talking about current things that happen in our society right now, we have a conversation, pretty important, I think, about the effects of government spending on GDP. And given that we had a drop in GDP, if we believe those numbers, of course, in the fourth quarter, have you done any similar tests as of what was for the component of GDP leading that drop? And if not, is that observation too soon to do?
Well, there's certainly a lot of uncertainty about the last quarter, but no, I stopped back in the second quarter of 2012, so I haven't updated this. I'm not trying to keep it up to date, but that's one of the issues in this game, is that these numbers do change over time. You know, they get revised and so on, and so if you're actually in the business of short-term forecasting or even long-term forecasting, as I mentioned, knowing where you're at is very important, and knowing where we were at in the fourth quarter is a lot different than looking at the fourth quarter, first release. There's new information coming out every week about what was going on sort of back then. And that's what folks who are in the forecasting business really focus a lot of attention on, and I would say appropriately so. One of the reasons I decided to get out of the forecasting business. All right, one more question, if there is one. Yeah.
Talking about Black-Litterman, I thought that there was formulas that was basically a combination of market cap and views. What was the follow-up work that was done to kind of study that?
Oh, the reference? Hay and Litterman, H-E and Litterman. Okay, that was a simple one. So, all right. Well, thanks very much.